Let's just wait for maybe another 5-10 minutes to see if there are people. So how's your project going? How about the design and stuff? Your labs, the lectures, do you have any questions about that? I received some emails regarding the homework. Regarding 4, but since I didn't teach that one, so I didn't really look into the Lab 4 yet. I will do my best to look into that and get back to you guys.
For lab 4, for some reason, the 5-volt thing won't really go inside.
I'm sorry?
Like, I don't know how to describe it. The 5-volt,
The 5-volt.
it
Yes.
won't go inside the breadboard. Like, it's positioned in such a way, like, I think since there's like 3 stems in one side, 3 pins, it's weird and it won't go in. And if I push it in, it's kind of loose and it falls off, or like it looks like it's gonna break.
So you mean the digital pin number 3? Is that the pin you were talking about?
Not sure what to call it.
The pin number 3, right? The pin with 3.
I think she means the relay.
Oh, that one. I think I'll need to look into that. I'm not sure what was a task for Lab 4 yet. I need to look into that. I thought you said that was on Arduino, because you can change the pin 3 to pin 9, 11, as long as that's a PWM pin, that'll be fine. Okay, it's 2:05. Let's get started. So for today's lecture, we are going to talk about the final project. Again, the omni-axle, the elbow exoskeleton. And here is the outline. We've already done the project overview, the background introduction, the biomechanics, the hardware, software. So for today's lesson, we're going to talk about the control system. So in this chapter, we will develop and implement different control systems that define the exoskeleton's behavior. To do so, we will define a set of rules of how the robot should act and react when worn by a human, pack those rules into some equations, and implement them on our Arduino microcontroller. The first part would be the introduction of control system. So what are control systems? Generally speaking, the control systems are a set of rules and algorithms that define the behavior of technical systems. They can be found in many technical systems to control many kinds of variables and keep it to a desired value. They control the fast and precise movements of the robot that assembled your car. They come along in the form of the autopilot that flies you to the Caribbean, and they keep your self-driving car aligned in the street at a constant speed. And in our case, the control system is responsible for the amount and timing of support provided to the user by the exoskeleton. So in order for a control system to work, sensors and actuators are needed. We've learned two sensors already. The sensors provide information about the state of the system. For example, the pulse and movement velocity of the robotic exoskeleton, and actuators can be used to react to the measured state following a predefined rule, the control algorithm. And here is a control diagram. Typically, control systems are represented by a control diagram. As shown here is a control diagram of a generic control loop. So can anyone tell me, is this a closed loop or an open loop?
Closed.
Yes, exactly. This is a closed loop. It's very easy to tell because you can see there is a loop with, yeah.
A sensor.
So on the left part, I'm sorry, there was a question?
Oh no, I was just trying to complete your sentence.
Okay, so on the left part, that is a desired value of a variable or system state, such as velocity. This is compared to the values measured by a sensor, which is this one, at the bottom of the diagram, the feedback loop. And the difference is calculated at here. That will be the error. And this difference is then sent to the This difference is then sent to the controller that adjusts, for example, the motor current, opens and closes of a valve, or executes an action to push the system, which is called the plant. In this case, that will be exoskeleton and user towards the desired value. After this input goes through the plant, the sensor measure again if the desired value is achieved, and the control reacts accordingly. This is repeated over and over again to put and keep the system at the desired value. The desired value can change over time, and the job of the controller is to make the system follow these changes. And for the controllers, there are high-level controllers and low-level controllers. And normally, they are distinguishable. The high-level controllers, sometimes called a control strategy, are a set of rules that defines, for example, in which situation the exoskeleton provides assistance force or execute a guiding movement. The high-level control can include a user intention detection to ensure that the exoskeleton support suits the user's momentary needs. And the lower level control system is responsible for the individual joints and actuators providing that desired support. So it is not uncommon in robotic exoskeletons that the user or a second person remains at least partially in control of the high level control system. For example, by controlling the exoskeleton manually by pressing control buttons. However, there are several approaches for exoskeleton to be autonomously detect the user's movement intentions and support needs. For example, by measuring the user exoskeleton interaction force or the user's muscle activities. The two following examples will help illustrate how the behavior of a robotic exoskeleton is defined by its control systems. The first example would be a control system of a gait restoration exoskeleton. So to control an exoskeleton for gait restoration in users with paraplegia, manual control inputs combined with a position controller are used. As the user's legs are completely paralyzed, the exoskeleton has to provide all the power required to move them. So in this case, the higher level control is implemented as manual control by the user. Buttons located in the handles of crunches that are required anyway for balancing are used to select and initiate movements manually. Different types of movements recorded and stored in the exoskeleton's control system, and this recordings provides the desired angle trajectories for each of the actuated exoskeleton joints. The movement is triggered by the user. The low-level joint position controller executes the recorded joint angles, replaying the movement. Then the exoskeleton automatically continues to execute consecutive steps until stopped by the user. Each step can be triggered manually by the user, who then remains in command. So I think this is pretty easy. It's like we got several different files, which we call them profiles. And when you are doing a certain tasks, you just choose this profile and implement it to the exoskeleton so that it will do the operation accordingly. And now that's the second example, which is the control of a work assist exoskeleton. So the second example is an upper body exoskeleton that supports the user when lifting heavy objects. The device is connected to the user's back and a hip like a backpack, and it relieves the user's arm when lifting and carrying a payload. To detect when the user needs support, sensorized gloves are used in high-level control. A pressure sensor in each palm measures when the exoskeleton user is carrying a heavy object, and only then a desired vertical assistive force is activated. And in this case, we are using a sensorized gloves, but in some other cases, when there are no gloves, we can detect the force on the arms. We can detect the position of the upper body, and there are a lot of ways to detect whether we are raising our hand, we are carrying a heavy object, or we are doing some other tasks. There are a lot of ways, and here it's just giving us a very brief introduction and the most basic talks necessary in each arm joint to provide the desired support. This desired joint torque are then sent to the low-level torque controller of the joints. And then they take it from there. As in every control system, this cycle is then repeated to reevaluate if the situation has changed. So again, measure the force, decide what support is necessary, and update the input to the low-level controllers accordingly. This is usually done very quickly and repeated many times every second to ensure that the exoskeleton will react quickly to changing users' need. Otherwise, you can end up with a slow device that provides inadequate support. How often such a cycle is repeated is defined by the control frequency, which is usually somewhere between a few hundreds or a few thousand times per second, hertz. And typically, the low-level control is faster with higher frequency than the high-level control to give the joint controller time to execute a command before a new command is received. And now let's talk about the common control approaches. As a part of a very large world of control systems, Let's take a look at a common low-level control approaches used for exoskeletons and other haptic devices. They mostly differ in which the variable or physical value is controlled. For closed-loop control, we can only use variables that we can influence and also measure. So the first one would be position control. A position controller controls a position, the joint angle of the exoskeleton. The controller focuses on only one aspect to move the exoskeleton joint to a desired angle. It will change the motor's torque until this desired angle is reached. And a control diagram for a position controller is shown here in this figure. This kind of controller is implemented in our servo motor, and it takes care of the low-level joint position control. This is why we can simply send a desired position to the servo motor. The onboard controller makes sure that the motor moves to the commanded position. Position control systems are very useful to support rigid guided movements or to limit the range of motion of a user, which we'll talk about that later in the virtual wall. And then we have the force and torque control. A force controller or a torque controller directly controls a force or a torque. A torque controllers try to keep a predefined desired torque without regard to the angle. Thus, in our case, if the user applies a torque that is higher than the desired joint torque, the exoskeleton will move. It's kind of a trigger. A closed-loop torque controller requires force or torque sensor. It also requires the ability to directly change the force applied by the plant, for example, by increasing or decreasing motor current. Force and torque control systems can be very useful to provide support, for example, an upward force to assist lifting without restricting the movement of the user. And then we have this impedance and admittance control. So in an impedance controller, position is measured and force is controlled. In an admittance controller, the force is measured and the movement is controlled accordingly. So they're pretty much, they're very similar, but apparently the control variable and the measured variable are different by the impedance controller and admittance controller. So we have a force sensor to measure the interaction force, and the low-level servo controller is a position controller. Thus, we will use admittance control in our exoskeleton. And in such an admittance controller, this rule often imitates the behavior of a mechanical system, the spring, the damper, the mass. As a simple example, you can think of a controller simulating a mechanical spring. When no force is applied and measured, the robot stay where it is. When a force is applied, the robot moves from its initial position by a distance that is proportional to the force. Thus, the robot behaves as a mechanical spring with a defined stiffness, even though there is no physical spring. So the impedance and admittance controller in between of the position and the force controller and they are often used when a force sensor to measure the interaction
What happened with him?
Hello.
Hey, what happened?
Yeah, you got cut off.
So where did I lost the connection?
I think the slide before this, it was going on and off.
Oh, okay.
Yeah.
So basically, these two pages is telling us that impedance and admittance control is a combination of the position and the force controller. And because we are going to use the admittance control, which is the input is a force and the output is the position. That's pretty much everything we talked about in these two pages. And here is a simple example. So you can think of a controller simulating a mechanical spring. When no force is applied and measured, the robot stays where it is. When the force is applied, the robot moves from its initial position. Sorry, let me the students see. Okay. So the robot stay where it is. When the force is applied, the robot moves from its initial position by a distance that is proportional to the force. And thus the robot behaves as a mechanical spring with a defined stiffness, even though there is no physical spring. And we can see this is the control algorithm. The difference between this one and the position controller would be this force error we input to this admittance controller, and which will give us a desired position that input to the position controller, and then input to the plan. I'm sorry, the background noise is a little bit too noisy. Thank you. And now let's talk about this tutorial about control system. So now you have been introduced to the basics. We can start implementing different control systems on the exoskeleton and finally make it do something. All of the controller presented in the following will be integrated into our Arduino software, Arduino IDE. And as we mentioned earlier, only variables that we can influence. I'm sorry? Was there a question? Okay, as mentioned earlier, only variables that we can influence and measure can be controlled. So in our exoskeleton, the value measure are the joint angles. And the joint angle can be measured by the motor's potentiometer, which I think you've learned in the lab of servo motor. And the interaction force with the force sensor, which we also learned. And the values we can control with the motor's integrated servo controller are related to the motor's movements. Hence, we can control the position, the velocity, and consequently, for our exoskeleton, we can only implement a position controller and an admittance controller. If we would like to implement an impedance controller, we need a motor that allows direct torque control. And so, attention, after implement a new controller, always test it first without your arm in the exoskeleton. This is very, very important. The motor is not very strong and it should not be able to hurt you, but better be safe than sorry. So simply fix the exoskeleton's upper arm segment to a table or another convenient object, switch the exoskeleton on and see what the controller does. You can still move it around by hand, hold it at the lower arm interface. Always test your controllers first to make sure you did not, for example, accidentally invert a sign and the exoskeleton starts to moving in the wrong direction, because that will be very, very dangerous. In our case, like we said before, the motor is not very strong, not very powerful, but things could go wrong. In the future design, you might use some very strong motor. For example, you might use some very strong actuations, hydraulic, pneumatic. Those could be very dangerous. So always bear that in mind. Safety comes first. And here we got the tutorial of the position control. The position control one is to move the exoskeleton from 0 degree to 90 degree, elbow flexion and back. And the second one would be record and replay a trajectory. And make sure that the motor is connected for this tutorial. We do not need the force sensor yet, so you can disconnect it to reduce the amount of cables if you'd like. And the point-to-point movement. The first point controller that we will implement is a simple back and forth movement between the two different positions. To realize that, we will use several elements, the variables, counter, reps, the functions, setup, loop, delay. We've talked about that. And first we define two new variables. Those are on the line 6. The counter, it stores how many points to point movements we have already executed. The variable reps in line 7 is the number of repetition we want to execute. Otherwise, the program would run forever until you unplug the power supply. And in line 21, there is an increment operator plus plus. Applying it to our variable counter will increase it by 1. There is also a minus minus operator, but we're not using that right now. And next, we compare our counter variable with the reps variable using the equal sign operator. Note the difference between a single equal sign and a double equal sign. A single equal sign assigns a value to a variable, like in line 6 and line 7, while the double equal sign compares the two values and returns true if they are the same, or false if they are not the same. And we use the comparison in an if statement, which is in line 22. Because of the if statement, the following block of code, line 23 to 25, is only executed when the if statement condition is true. And in our case, until the number of repetitions reaches the value we defined in the beginning of the sketch. When that number is reached, the exit 0 command will end the program. If you want to restart the program after reach the desired number of repetitions, you can push the reset button on the Arduino board, which would be beside the power barrel. And for the first test, we strongly advise you to mount the exoskeleton to a table or similar stable support beforehand. Only after you check that the control works properly and that the movement is as intended, you can put the exoskeleton on and test it. Just let your arm be guided by the exoskeleton. You will realize that the motor power is limited and that you can easily stop the movement if you want to. This is yes.
I have a question. For the final project, do we have to write a report for this? All these findings.
Yeah, I think so.
Okay.
You can find the detailed information for the final project in.
It's due on the 16th.
I'm sorry.
It's due on the 16th. The report is due on the 16th.
Oh yeah. Thank you. We will wait. So you can easily stop the movement of the exoskeleton if you want to. This is perfectly fine. As a motor of this side, it will always be limited in power, but it is much safer to operate, and you can feel the interaction and test different controllers. Professional exoskeletons work in a similar way to this precision controller, but with stronger and much more expensive actuators that are able to move paralyzed limbs and assist with high payloads. But we don't need those. And quite frankly, because this is a very not so strong motor, so it has a better backdrivability. And pre-recorded trajectory. The second precision controller that we will implement is to record the trajectory of a real human movement and replay it with the exoskeleton on demand. So this program introduces many new aspects of the Arduino microcontroller, most of them linked to memory and data management. So you may already ask yourself why an exoskeleton would execute a point-to-point movement. Well, this is perfectly acceptable behavior for an industrial robot that executes a pick-and-place task. The applications for human movement support are limited. It makes much more sense to record the trajectory of a real human movement and replay it with the exoskeleton on demand. To do this, we will write a program that records a trajectory and saves it in the Arduino memory, and then the program will replay this trajectory. And so let's first look at Arduino Uno's 3 memory types. So the first one would be flash memory, where the compiled Arduino sketch is stored. The RAM, the random access memory, RAM, where the program creates and manages variables when it runs. And EEPROM, electrically erasable, programmable, read-only memory. Memory that you can use to store information that is saved when the board is turned off. And you probably know at least some of these memory types on a computer or smartphone, but in those devices, you usually have much more memory available to store data or for your programs to execute. In a PC or phone, memory sizes of megabytes, gigabytes, or terabytes are much more common than the few kilobytes or hundreds of them we have available on a typical microcontroller. This is because microcontrollers are stripped down to the very basics we need to execute our small programs. And microcontrollers do not have any operation system that already requires gigabytes of memory. And we also do not store hundreds of vacation pictures on them, so we don't need that much of storage. And for flash memory, The flash memory is used to store the compiled program. You access it through the Arduino IDE when you load your compiled sketch onto the microcontroller. The program is stored there safely. Even if we unplug the Arduino, this is the reason why the exoskeleton will immediately run your last program when you switch it on. The RAM memory is used to store information while the program is running. The runtime called all the variables that we define in our program are stored here. Different variables require different amounts of space. For example, a byte variable requires 1 byte of memory. An integer variable requires 2 bytes, etc. Thus, if you define too many variables, you might run out of memory. The RAM memory is erased when the Arduino is switched off, as it needs power to store the information. And the EEPROM memory can be accessed from the program to store data as well, but in contrast to the RAM memory, the data stored will remain there when you switch the Arduino off. Therefore, it is suited to store data you plan to reuse in another session. When you compile and upload your program, you can find information on how much of the flash memory and dynamic memory are used by your program and how much are available within the Arduino IDE. And here is a program to record and replay a trajectory. With the memory discussed, let's walk through the program step by step. First, we include the EEPROM library, which is Lite2, which provides the functions to access the EEPROM memory. Next, we define 2 constants with a processor directive defined. That's in line 4 and line 5. This is a little different to defining a constant variable. For example, constant in int samples equals 200. That's different. When using the define directive, preprocessor replaces all mentioning of the defined constant in the source code with the defined value before the IDE sends the code to the compiler. By replacing it in the source code before compilation, the constant is hard-coded into the program that is stored in the flash memory. This saves RAM during runtime. A potential disadvantage of using preprocessor directive is that it can create bugs that are very hard to find, especially in larger programs where you might accidentally reuse a previously defined expression in your code as a variable name, which is then replaced by a constant value. If memory is not an issue for your application, you can use normal constant, but now you have a choice. The constant we define are a fixed sampling period sample delay equal to 25 milliseconds. This means that every 25 milliseconds we record a new trajectory point. This second constant samples defines how many trajectory points we record. If you do the math, you will find that we record 5 seconds worth of trajectory. You can adjust these values, but keep in mind that the EEPROM capacity is limited to 512 bytes, and we need 1 byte per trajectory point. So how many trajectory points we can have at the most? So at most we can have 512 bytes for trajectory points. And next you will find that not all the code is in the main loop, 15 to 21. Rather, we define 2 functions and call them from within the main loop. You can already see that by doing so, the structure of the program is easier to follow. And if we took a look at the record trajectory function, which is in lines 23 to line 32, there is a for loop inside, which is repeated once for every sample we want to record. That is done by using the loop counter, which is initialized to 0. In every cycle, if the condition is true, the code inside the for loop is executed and the loop counter is incremented by 1. This is repeated until the condition is reached. That is until we record all the trajectory samples. Within the loop, the position sensor value is read. That's in line 26. In line 27, you will find our mapping function between angle servo voltage and motor position compared to what we learned before. And the idea is to not store the angle sensor value in the EEPROM memory, but rather the corresponding motor command that we have to send later to replay the trajectory, as the mapping function returns a value that is between 0 and 100. Or similar values. Depending on your mapping function, we can store the motor position. Just wait a second. So as a mapping function turns a value that is between 0 and 100 or similar values depends on your mapping function, we can store the motor position value in a byte variable, which is 8 bits. This byte is stored in the EEPROM in order. In general, the memory is accessed by a number that defines which of the 8 bytes we want to write or read. Then we wait for the defined delay time before we record the next sample, which is in the line 29. And this function finished by displaying when it is done recording the trajectory. That's in line 31. And our second function, replay trajectory, which is in line 34 to line 44, is very similar. It reads out the recorded trajectory sample by sample and sends it to the motor at defined time intervals. The only novelty in the for loop is that we read the stored byte at the momentary EEPROM address, which is in line 38, and then send it to the motor, which is in line 39. When the entire trajectory is replayed, we have to detach the motor in line 43 to deactivate it. Otherwise, its servo position control system would remember the last position and stay there, preventing us from recording another trajectory. As a general comment, note that this program only provides the very basic functionality of writing and reading EEPROM that we need for our example, and several features can and should be added to improve the code, such as preventing exceeding the address space of the EEPROM in case you accidentally record more than 512 data points, and consider it your homework to do these improvements when you use the EEPROM storage capabilities. And you need to notice that when you're doing your final project. And now we talk about the tutorial admittance control. And make sure the interaction force and then control the exoskeleton's movement accordingly. In a simplified way, you can see it like this. If the force is too high, more than we desire, we move away from the user. If the force is not high enough, we move towards the user. And an implementation of such an admittance controller will measure the force as before and then control the motor's movement. In this sketch, you will first find that we now have two force variables in line 6, that's force IS, and force desired, that's in line 7. The first one we know already. This is our measured force. And the second one is the force that we want the exoskeleton to impose on the user to provide support. And in line 8, we have the variable position desired that we initialize with an arbitrary value within our range of motion. And in line 9, we have our control gain. The higher it is, the more responsive the controller becomes. This can be good as it reacts more actively to adjust the force. On the other hand, a high control gain can quickly result in unstable system behavior. But there is something we need to notice, that this one is not using the HX711 chip, but we are using HX711 chip. So it's going to be slightly different from the pin we're going to use to the variables, but we've already uploaded that to the Dropbox. So you can just use that instead of this one. But still, you need to include those servo.h files. And the loop starts with our force calibration, which is in line 17. At this point, it is important that we offset the force to know its direction. You can also include any additional calibration you might have prepared in a previous, like we learned in the load cell chapter. So now we add a delay of 10 milliseconds. That's in line 18. This delay will affect the control frequency. And that is how often the entire control loop is executed. You can change it later for testing. And line 19 is our admittance control algorithm. You can see that we calculate the differences between the force that we measure and the force that we desire, multiply this difference by our gain, and then adjust our desired position accordingly. And last, we send the new desired position to the position controller of the servo motor, which is in line 20. And if you want the exoskeleton to just move out of the way, set the desired force to 0. In this zero force control or transparent mode, the user should be able to move freely without being hindered by the exoskeleton. The exoskeleton is basically trying to move out of the way. The term zero force control is a little misleading because you actually have to measure some force to know the intention of the user to move in a certain direction. Usually, the quality of such zero force controllers are judged on how little resistance the user feels. For example, which means how small the interaction forces are in this control mode. The quality of this mode and the control system in general is affected by many factors, including mechanical design, the mass, the friction, etc. of the exoskeleton, and the speed of the actuator, and the frequency of the control system. You'll find that with our setup, the zero force control reacts rather poorly. Try to increase or reduce the delay, which is in line 18, to test how the control frequency affects the behavior and the quality of the control system. And remember, always test first without your arm in the exoskeleton. Also increase and reduce the gain, that is in line 9 from the last page, and feel what happens. And next, you can change the desired force to another value and see how the exoskeleton behaves. And here is a hint for the design. By design, the force sensor is located very close to the lower arm cuff. This should ensure that the interaction force can be measured. If you interact with the exoskeleton in a way that the force sensor cannot measure it, for example, by trying to move the exoskeleton at the interface motor sensor part, the admittance control will not react. And now let's talk about this virtual wall feature, which we actually talked about. So now we will implement a controller that will allow you to move in a certain range, but will prevent you from moving beyond that desired range of motion, which is called hyperextension, if you still remember what we learned in the biomechanics chapter. So thus, the exoskeleton will try to limit and guide your movement to stay within a certain range. This can be very useful, for example, in rehabilitation or motor learning, to prevent users from executing undesired or even harmful movements. We will implement this controller by using a zero force controller and two threshold values, one on each side of the ROM range of motion, that limit the possible movement in each direction. So as a simple example, you can think of a controller simulating the, there are two stops on each side of this. Just instead of the actual stops on each side, we are limiting the range of motion of the motor. Let's put it that way. And here is the virtual wall controller. The threshold are defined by two integer variables in line. Okay. The threshold are defined by two integer variables in line 10 and 11. And adjust these values in your setup if necessary, because everyone have a slightly different range of motion. But normally that would be it. And while you are trying your exoskeleton on, you can feel it and read the numbers on your Arduino and then set up this maximum angle and minimum angle. So the virtual wall behavior is implemented with two if statements, which is in line 22 and then 23, that check if the new desired position out of the admittance controller exceeding the defined threshold. If the desired position is out of the defined range, the virtual wall become active and adjust the desired position to the maximum or minimum value before they are sent to the servo control. The resulting behavior will feel like walls, as the exoskeleton will prevent you from moving beyond the predefined range. You can see that the second statement is an else if statement, which groups it together with the first if. This means the else if will only be evaluated if the if is not already true. This makes sense here because only one of the two conditions can be true at a time. This can save computation time because if there were two simple if statements, both would always be evaluated in every cycle. And as we mentioned, because this motor is not that powerful, so this wall-ish feeling may not be that strong. It depends on how you how you sense the force it provides you. But the thing is, with this wall, it's definitely way safer so that you won't hurt yourself. And with all those tutorial on the control systems, Here are the future approaches. We learned a lot from this final program. We learn sensors, we learn actuators, we learn controls. And with all those we've learned, you can now implement that into your final project and make an exoskeleton that can actually work. And you will feel very proud once that been produced. And speaking of which, we almost finished the 3D printing process, and we are planning the pickup of the exoskeleton parts next Monday or Tuesday. So please make arrangements accordingly. Santa will then send a detailed email regarding how and when to collect the exoskeleton parts. She will send you guys an email about that. So just in case if you have any questions, please don't hesitate to ask us.
How do we collect the components for not the 3D parts, the load cell and all that?
Oh, they will all come together. I'll give you the 3D printed parts and
Okay.
the load cell, the motor, and everything.
Okay. All right. No problem.
Yeah, they will be in one bag.
And now also you mentioned that you want a CAD drawing of the exoskeleton. What do you mean by that?
So because there are two parts of this final project, the first one is you design the hardware. The second part is you do the control algorithm, so
Right.
that you don't just have a frame, but you got an exoskeleton that actually works.
Okay.
However, because due to the pandemic thing, you are not allowed to come down to the campus, and because of the 3D printing is very time consuming, it's not very possible for us to 3D print out every single one of your design. So we decided that we will design something that is very standard, very simple, very basic as well, that can only execute the tasks we ask you guys to do. So it's not a perfect design, but at least it meet all the requirements in this final project. So we will give you that 3D print part.
Okay, but we
That-
still have to submit a three-dimensional. Okay.
Yeah,
And that's
because
25th.
that will be your design part, and then so as I said, there will be two parts. One is designing the hardware,
Right.
part. The other one would be the control. So you send us your CAD model. That will be the designing part.
Right. Right. Now that's due on the 25th,
24th.
correct? Oh, 24th?
I think that will be 24th,
Okay.
11,
All right, no problem.
59 p.m. Yeah.
All right, cool. Thank you.
Do you guys have any other questions? Do you have any questions regarding the final project, the homework, and in general?
Oh yeah, for the homework, I believe the second article wasn't in the folder itself, so I just Googled it.
Okay, that'll be fine too.
Yeah, all right.
It doesn't really matter because the reason we put that file in the folder is because we think it'll be easier for you guys to get access to the to the paper. But sometimes we may forgot to upload some of them.
All right.
Hey, I also had a question. When is the homework assignment due?
So for each homework assignment, you can find the due date on the slideshow that assign you with the assignment. Because each assignment would have a different due date. Normally, I would
Yeah,
say
I don't think it was on this one.
so normally that will be the 3 weeks from the assignment date, the assigned date. For example, if we have some homework today, we don't. But if we do have some homework today, assigned today, then you will have 3 weeks to complete that.
Professor, do we leave the room now? Or?
I'm not a professor, just call me Bowen. But if you don't have any questions, I think you can leave now. But if you do have some questions, you can just ask. Or if you prefer to email us, that would be fine too.
Okay, thank you, Bowen.
Thank you, Visual.